is right here. So it's question number 1. It says what is the major product from the reaction shown? So we have 1-ethyl cyclopentene, and we're treating that with water and acid. Right? So what are we doing? All we're doing is we're just doing a Markov-Nikov addition across that double bond, right? You know that the first step is going to be the proton transfer. So I'm not going to draw the whole hydronium molecule, but you know the first step is just a proton transfer like this, which would give us the most stable carbocation, right? Then you have water come in as a nucleophile, another proton transfer, and you're going to end up with this compound where you end up with 1-ethyl cyclopentanol, which is this compound right here, B. So you should know Markov-Nikov addition of water across a double bond. If we take a look at question number 2, it says predict the major product of this reaction. Remember that when you see B2H6, that's the same thing as saying borane, THF, and I mentioned this briefly when we looked at hydroboration oxidation. So not only are these the conditions for anti-Markov-Nikov addition, in terms of regioselectivity, so that means the hydrogen should be attached here, the hydroxyl should be here. Well, if you look at A, you have the hydroxyl in the right place. If you look at B, you've got the hydroxyl in the right place. If you look at C and D, we'll see the hydroxyl's in the wrong place, and at D, that's just plain totally wrong because it's a diol. But then the question becomes, is it A or B? Could anybody tell me which one of these would be the correct product? Would it be A or B? Well, we have to remember that not only is hydroboration oxidation anti-Markov-Nikov, it also proceeds with syn addition. So syn addition of the hydrogen and the hydroxyl. And so the correct answer is going to be A, because this one is correct in terms of it being anti-Markov-Nikov regioselectivity, but also the product that results from syn addition, whereas B is the product that would result from anti-addition. And so A is the correct compound. Question number 3 says, what would be the best method to carry out this transformation here? So we start with this compound. So this is what, 3-methyl-1-butene. So we're starting it with 3-methyl-1-butene right here. And we're just doing a Markov-Nikov addition across that double bond. But I want you to take a close look and see if you can tell me what would be the best conditions for doing the Markov-Nikov addition of water across this double bond. Yeah, it's going to be D, to prevent a rearrangement. Right? If we just used A, we would end up doing a carbocation rearrangement, wouldn't we? All right, if I just draw out the starting material, which is just this compound, right? After you do the proton transfer on the first step, you would end up with this carbocation, which is going to undergo a proton transfer like this to give you this carbocation, and then water's going to come in, and you would actually end up with this compound. Okay, we have the hydroxyl here, so that's not right. B is an anti-Markov-Nikov addition of HBr followed by sodium hydroxide. So after the first step, you just do an anti-Markov-Nikov addition, you would end up with this compound. And then after you treat that with sodium hydroxide, well, hydroxide is a strong base, but it's also a strong nucleophile. You would get an SN2, and you would end up with this compound, which is also not the correct alcohol. C is anti-Markov-Nikov addition. First, you're using borane, and then in the second step, you're using hydrogen peroxide followed by sodium hydroxide. So that would also give you the anti-Markov-Nikov product. It's D is going to be the correct answer because this is a Markov-Nikov addition, but we avoid the carbocation rearrangement. So you would take this compound, you treat it with mercuric acetate in water, followed by sodium borohydride, and that's going to give you the Markov-Nikov addition, and you get no rearrangement, right? Because you want to avoid this rearrangement at all costs. And again, so the correct answer would be D is the correct answer. Let's try question number 4. Where is it? Here it is. It says predict the product from the reaction shown here. So we're taking this compound, and the first thing we're going to do is, since we have an unsymmetrical alkene, we're adding HCl to it. So this is going to be a Markov-Nikov addition. Let's take a look. The rich are going to get richer, and what you're going to end up with is this compound. So I'm just going to draw the bond line structure of it, and you would end up with this carbocation, which is a secondary carbocation. And so this proton is going to undergo a hydride shift over to here to give us the tertiary carbocation, won't it? And we're going to end up with a tertiary carbocation. And so the chloride is going to attack the more stable carbocation. So we're going to attack here. And so we're going to end up with this compound. Oops, not that. There we go. And we're going to have the chlorine here. And so that is going to be A. So again, you have to be kind of on the spot in terms of your carbocation rearrangements and have to be able to figure out when they're going to occur. I'm going to ask you guys about question number 7. Let me find it here. Question number 7. Could anybody tell me what would be the best set of reaction conditions to carry out this reaction? Yeah, I agree. This is an anti-Markov-Nikov addition of water across a double bond. This is anti-Markov-Nikov addition. And so remember that B2H6 is the same kind of thing as borine THF. It's just borine in its dimeric form. So again, we have borine followed by hydrogen peroxide and sodium hydroxide. So this is just anti-Markov-Nikov addition of water across a double bond. B and D are both Markov-Nikov. B is Markov-Nikov with a carbocation rearrangement, and then A is not going to do anything. So there you go. The correct answer is C. Let's take a look at question 8. It says the addition of bromine to E3-hexene will give what? A meso compound, some enantiomers, 2 meso compounds, or 4 stereoisomers. Well, we're starting out with an E compound, aren't we, right? So remember that bromine or bromination gives you syn addition of the 2 bromines. And so if we have our 2 carbons like this, we're going to end up with 1 bromine on one side of the molecule and the other bromine on the other side of the molecule. So if I think about this carbon in red here, I'm going to have a hydrogen going in back, and then I'm going to have this ethyl group coming out in front, and that's this one right here. Whereas if I have the other carbon, if I label it in blue, I'm going to have the ethyl group. Let me draw it in a better angle. The ethyl group is going to be going up and back like this, and the proton is going to be coming. Shoot, that's not very good. There we go. The proton is going to be up like this. And so what kind of compound is this? Well, if you rotate this carbon-carbon bond right here so that you put the 2 bromines in the same plane, you'll see that this is actually a meso compound. I'll prove it to you. If you draw it with the 2 bromines in the plane, and there's not a lot of room here, but you end up with this ethyl group coming out like this, and then this ethyl group, when it's rotated so that this is up here, this ethyl group is going to be coming out like this. And so this has a plane of symmetry, 2 chiral centers. So this is a meso compound. So we end up with a meso compound in this particular case. We take a trans alkene like this, and we do, did I say syn addition when I meant anti-addition? Nobody stopped me, so anti-addition. All right. Let's take a look at question number 14. So question number 14 says, what's the major product of this Diels-Alder reaction shown? We have our diene here, and we have a nice dienophile, right? And you should be able to draw the curved arrows for this reaction mechanism. So we're going to do a bond here, we're going to make a new bond here, and we're going to make a new bond like this. So this is going to give us a bridge system. This six-membered ring is going to be positioned like this, okay, like that. Then you have one bond to a carbon like this. So since this dienophile is trans, you're going to have one of the nitrile groups coming up and the other one going down like this. Okay, so if you look at all the answers, you can see that A is the correct answer. It's definitely the one that's the closest. I mean, B has two double bonds. That's just totally jacked up. C and D have nothing to do with what you would end up with at all. You can see how they kind of draw their wedges a little funny here, right? This one is kind of drawn pointing down, kinda, and this one is drawn pointing up, kinda. This one's not the best way to draw it, in my opinion, but either way, you can clearly see, oops, and I forgot my double bond, didn't I? I forgot to draw in the double bond that's formed right here. So either way, this is a Diels-Alder reaction, and you should be able to identify the product of a Diels-Alder reaction. Question number 16. I'm going to throw this out there to my students. I want to make an epoxide. Could anybody tell me what are the best conditions to make an epoxide? Yeah, it's going to be C, because you remember that this is a peroxy acid. Peroxy acid. This is actually, yeah, a generic peroxy acid. An example would be something like MCPBA, okay? And that peroxy acid makes a peroxide. And so this is the correct answer right here. All right, let's move on from there and move on to talking about some carbonyl chemistry. So let's take a look at some carbonyl chemistry for a minute. And I thought we would start with this question right here. What is the expected product of this reaction? I'm taking cyclopentanone and I'm treating it with hydrazine. This is hydrazine. There we go. Could anybody tell me which one of these would be the correct answer? And this is something that we looked at in detail this summer. Yeah, it's going to be A, isn't it? Right? This is a hydrazone. Hydrazone. Okay, and so the correct answer is A. None of the other ones are anywhere even near correct. I mean, this is an imine right here, but that has nothing to do with this particular reaction. So you would end up with a hydrazone in this case. Take a look at number 6. Where is it? Over here. I'll just zoom in on the question first. It says you're taking cyclohexanone, you're treating it with ethylene glycol. Everybody should recognize this molecule, right? This is ethylene glycol or antifreeze. TSOH, that's tosic acid. TSOH is the same thing as toluene sulfonic acid. So that's this guy, which is a sulfonic acid, which is a very strong acid. Okay, so we've got toluene sulfonic acid, and C6H6, that's just benzene. So C6H6 is benzene, which is just the solvent in this case, and you're heating it up. Okay, so I'll let you guys take a look at the answers and if anybody could tell me what the answer would be here. What would we get in this particular case? Taking a glycol or a diol, treating a ketone with a catalytic amount of acid. Right, this is the reaction for an acetal formation. Right, so we would end up with an acetal, and we end up with a cyclic acetal in this case. So this is acetal formation. Okay, and if you remember, we even used this acetal as a protecting group for a carbonyl. And so make sure you know acetal formation. All right, question 14. I love these kind of questions. So always long questions whenever they say, which of these would not form the following alcohol after aqueous workup? So aqueous workup just means like you've got this, and then these are all the first step of the reaction, and then it means that step 2 is just like put water in it. Okay, that's all it means by an aqueous workup. I'll give you a second to look at this one. I want you to think about this one. Can anybody tell me which one would not give you this compound after aqueous workup? There's one of them that's way off in left field. There's a big mistake in one of them. Yeah, the answer is D, isn't it? Right, you can see that A, B, and C will all give you the right compound after a nucleophilic attack and a proton transfer. However, here in D, just count the carbons, right? You need to have 1, 2, 3, 4 carbons. I mean, D is a reasonable reaction. The problem is this nucleophile would end up attacking here, okay? And then you would end up with a total of 1, 2, 3, 4, 5 carbons when you only need 4 carbons. So you'd actually end up with too many carbons. And so the correct answer is D. You end up with too many carbons in this case, but all the other mechanisms are all going to give you that compound. All right, next one. Predict the product from this reaction? Let's draw out the mechanism. So if we have phenolithium, we can regard that as a vinylic anion, again, which won't really exist, but we can think of it as being that way. So we have a good nucleophile and we have a good electrophile in our aldehyde. So what's going to be the intermediate that we're going to form? I'm just going to replace the aromatic ring with pH, and we're going to have our oxide like this. Then in the next step, we treat that with a source of protons. And so you're going to end up with this compound. You end up with the hydroxyl here. And there you have it, my friends. And so the answer is going to be B. Just a very simple nucleophilic attack followed by proton transfer, right? The first step here, this is your nucleophilic attack. And then you have the proton transfer down here. And that's, a pretty basic nucleophilic attack question. Nucleophilic attack on a carbonyl. All right, let's try question number 17. It says, which reagents will accomplish the conversion shown? So we want to take 2-cyclohexenone, and then we want to convert it to this 3-methylcyclohexanone. I'll just throw that out there to my students. Can anybody tell me what would be the best reaction or best reaction conditions here? So if you think A is not going to do anything, right? If you were to mix this compound and iodomethane, nothing is going to happen, right? If you react it with a green yard is going to give you 1,2 addition, right? If you use B, you'd end up with this, which would give you 1,2 addition. That's not what you want. So that's not going to work. So we can cross this one and this one. Same thing with methyl lithium. It's just going to do a nucleophilic attack at the carbonyl carbon. But remember, this is a Gilman reagent or a cuprate. Well, cuprates do 1,4 addition, 1,4 addition when we use a cuprate. So this is a Michael addition. And so to do this, we would use a cuprate to do that. It's a softer, what we call a softer nucleophile. Next, I wanted to take a look at this one here. This deals with Wittig chemistry. It says, what is the product of this reaction sequence? So whenever you see triphenylphosphine, so that's what this represents right here. This is triphenylphosphine, this compound, which is a good nucleophile, right? We know that. So what's going to happen is you're going to start with your starting material, which has an aromatic ring, then a CH2, then a chlorine. So that's benzyl chloride. I told you many times this is a very powerful electrophile. So we're going to treat that with triphenylphosphine, and we're going to get a nucleophilic attack, loss of our leaving group. That's going to give us our ylide. So let's draw out the ylide, which is going to look like this, like that. Okay. Then we have potassium Tbutoxide, which is going to be a base. So we have potassium Tbutoxide, which is going to do a proton transfer here to make the ylene, or the Wittig reagent, whatever you want to call it. So we have a negative charge here, Then we have the positive charge here. And I told you that this is called the ylide form. And then when that reacts with the carbonyl, and I'm kind of running out of room here, but you're reacting it with this compound. So this is, it's called benzophenone. Anyhow, all you're going to do is make a connection. You're going to break this bond and add this piece onto there. So you're going to end up with, and I know there's not a lot of space here, but you're going to have two phenols, right? Then you have a double bond, okay? This carbon, which is right here, and then you have a phenyl attached to it, like this, okay? And then you have a hydrogen here, and you can see that this is the correct compound, right? This is a Wittig reaction. So make sure you know the Wittig reaction, and you know the ylide and the ylene. And there you have it. So the first thing I didn't mention is the phosphonium salt, but that's because I left the chloride out. But this would be the phosphonium salt here, and then this is the ylide here. You don't even have to draw the ylene anyhow, but this is Wittig chemistry, and make sure you can draw the mechanism of this reaction. Just a straightforward Wittig reaction, which we talked about in detail this semester. Question 21. What is the product of this reaction sequence? So we have more Wittig chemistry here. We have a phosphonium salt right here, and we're treating it with C4H9Li. That's the same thing as butyllithium, okay, which we've talked about many times over the course of the semester. It's a really strong base. You can just write out like this: 1, 2, 3, 4. Okay, very strong base. So that's going to rip off one of these protons to make our ylide. So we're going to go from the phosphonium salt to the ylide. I'm going to draw the ylide, which is going to be this. So now I'm going to replace these with pH. So we've got pH 3, our phosphorus with a positive charge, and then we've got this. So this is our ylide, okay? And then we're going to react it with this molecule, which is this guy, okay? Which is a Michael acceptor, and I don't know if that's what they're trying to trick you on or something. But again, in a Wittig reaction, you're going to react with the carbonyl carbon, and you're going to end up adding this group onto it. So you're just going to end up with this molecule. So let me draw it a little neater. So 1, 2, 3, like this. And there you go, right? Because you end up with this CH2 on top, and you can see that that is A. It's this molecule right here. They've just drawn the double bond. You know, they just rotated this bond here so that it looks like this. Okay, like that, but either way, it's the exact same thing. This section deals with nucleophilic substitution at carbonyl groups. So I had some picked out here. So this goes back to the carboxylic acids chapter. We talked about a lot of carboxylic acid chemistry, right? Here we've got an amide. Here we've got an ester. Here we've got an anhydride. And the last one is an acid chloride. Acid chloride. And it just asks you which one of these would react the slowest with aqueous sodium hydroxide. So which one of these would be the least susceptible to nucleophilic attack? And we talked about this in detail. Yeah, I'm not sure if that's an answer for now or not. But anyhow, right, we talked about the order of reactivity. If you remember, in that chapter, we started out by talking about acid chlorides because they're the most reactive. Then we went to anhydrides because they're the next reactive. Then we went to esters, and the last one that we discussed was the amide. We said these are very unreactive. Okay, it's not very good chemistry trying to do the hydrolysis of an amide and base. We said you can do it, but it requires really forcing conditions because amides are so unreactive. Question number 8 says, what are the products that you would isolate from these reactants? So we have an acid chloride and an amine, right? And this is just going to give us an amide. And I know that normally in our textbook, he writes excess, of the amine, but you can just assume that you have excess. So you'd end up with this compound where you have the carbonyl, and you have the nitrogen, and then you have the ethyl. So this is N-ethyl acetamide. So that is which compound? It's this one right here, D. So this, again, is just a nucleophilic acyl substitution of an amine on an acid chloride, reaction that we looked at 10 times at least in the carboxylic acids chapter. Question number 10. What are the products of this reaction here? So this is just the hydrolysis of an amide using hydroxide. Again, not a great reaction, but it will work, okay? And what would you end up with in this case? Well, let's think about it. I mean, you're in a strong base, right? And which bond is going to be susceptible to nucleophilic attack? If I draw the bond line structure out like this, the nucleophile is going to attack here, right, during your nucleophilic acyl substitution. So the bond that's going to break, if we draw this intermediate, you have the hydroxyl like this, okay? The bond that's going to break is going to be this bond over here after a proton transfer. And so you're going to end up with not a carboxylic acid, right? You're not going to end up with a carboxylic acid. If you're in a strong base, you're going to end up with a carboxylate. So it's got to be this product here. And of course, after a proton transfer, you would end up with the amine. So the answer is C. Just the hydrolysis of an amide base, and then the reaction we looked at in detail. Question 13. We want to take a carboxylic acid and convert it into a methyl ketone. How in the heck do you do that? I'll give you guys a second to look at this one and see if you can come up with an answer. Yeah, it's going to be C, isn't it? Right, after the first step, you treat it with thionyl chloride, and that's going to give you the acid chloride like this. Sorry, did I say C? Because I didn't mean C. That's not right. Sorry, I meant it's going to be B, right? Because if you were to use methyl lithium, you would end up with an alcohol in the end, right? If you were to treat this with methyl lithium, that's going to do nucleophilic attack, proton transfer, and you end up with a tertiary alcohol. So you have to hit it with a cuprate, right? So you would want to use the dimethyl cuprate is what you would use to do the substitution, the nucleophilic acyl substitution to make butanone. All right. So again, cuprates. So if you're unsure about your cuprate chemistry, make sure you review your cuprate chemistry. And this, again, is covered in chapter 21. Question number 14, a Grignard reaction. But now you're doing a Grignard on a lactone. Remember, a cyclic ester is called a lactone. So what happens when you treat an ester with a Grignard is it does a double addition, doesn't it? Right? You end up with two additions that occur. So if we draw our lactone over here, so again, this is question number 14. We have our lactone, which looks like this. And we're treating this with ethyl magnesium bromide. So we have ethyl magnesium bromide. I'm going to draw it out like this. The first thing is that you're going to get a nucleophilic attack like this, and we're going to end up with this compound. We still have this oxygen here. Now you have the oxide here. Ethyl group. So then you get, oops, anyhow, I should have drawn those in black, but whatever. So we're going to end up with this. So now we've got our 1, 2 ethyl. And we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And then we have this alkoxide over here, but it's not done, is it? Right? Since we have ethyl magnesium bromide, another equivalent of the ethyl magnesium bromide is going to attack again. So you get a second nucleophilic attack like this, and that would give you this compound. There you go. And then after two successive proton transfers, right, you treat it with water, you end up with a tertiary alcohol here, and you end up with a primary alcohol here. And so that would be the final product. You end up with two alcohols. And so if we go back to the question, you can probably solve this mostly by a process of elimination, right? You have only one compound that is a diol, don't you? And it's D. It's the only one, right? The ring is not going to be intact. That's for damn sure. And this is actually an intermediate, isn't it? Right? And that's going to undergo another nucleophilic attack. All right. So a little bit of green yard chemistry for you. Let's try another one of these nucleophilic acyl substitutions. If we want to just take this carboxylic acid and we want to convert it into an amide, what would be the best course of action here? This is a reaction, again, that we looked at many, many times. I know I keep saying that, but I remember going over these with you. Take a carboxylic acid and convert it into an amine, or an amide, rather. All right, this is very similar to a reaction that we looked at already. Yeah, the answer is A, isn't it? Yeah, you're going to make the acid chloride in the first step, and then you use the amine as a nucleophile. It's going to do a nucleophilic acyl substitution, and you're going to end up with the amide. Let's try one more from this section. This one is just the reduction of an amide. And this is another reaction that we looked at, the reduction of an amide. So reduction of an amide. And there's no mechanism for this in our textbook. No mechanism at all. All you really do here is you end up removing the carbonyl so that you end up with this compound. And you basically remove the oxygen and replace it with 2 hydrogens, and that's it. That's the reduction of an amide with lithium aluminum hydride. And so the answer is, let me make sure I get the right one here. It's D. I just looked at A, but A is missing that carbon. It just is removed. So the correct answer is D. There we go. All right. So let's move on from there. And let's take a look at question number 4 here. All right, it says, which set of reagents would accomplish this conversion? So I'm taking diethyl malonate. We talked about this quite a bit. Diethyl malonate. All right, and I want to just add an ethyl group to it. Who could tell me what the best course of action would be here? Yeah, absolutely. Absolutely. I would just treat this with sodium methoxide, which is going to be a strong enough base to deprotonate, right? Because we said the pKa here of this proton is around 9. It's a lot more acidic than if we just had a regular ester, which have a pK of probably around 20-ish. And so all you need is sodium methoxide to make the doubly stabilized enolate, and then you treat it with ethyl bromide, which is going to act as an electrophile, and that's just going to do an SN2 reaction, and you end up with that intermediate. All right. Here we go. So question 8 is, what would be the major product of this reaction? So we're starting out with butyraldehyde, and then we're treating it with just sodium hydroxide and water. I have a question for you guys. Would this be an aldol addition or an aldol condensation reaction? It's not going to be a condensation, because if it was a condensation, there would be heat. So there's no heat. And when there's no heat, it's just a plain old aldol addition. So I'll give you a second to look at it. Well, if it's an aldol addition reaction, it can't be A because here you have two carbonyls. Remember, in an aldol addition, we end up with an aldehyde and an alcohol, right? Right, so it's definitely not going to be A. It's definitely not going to be a B because that's not the product of an addition. But in C, it looks reasonable, doesn't it? Because in that case, you'd start out with this enolate, and that would do a nucleophilic attack over here, which would produce this compound. So I'll just kind of curve this bond here like that, 1, 2, 3, 4, and then we end up with this alkoxide. So 1, 2, 3, 4. And then after the proton transfer, so we do a proton transfer, and then we end up protonating here, and you can see that that is going to give you this compound here. I mean, this is the only aldol in here, right? Aldol. So as long as you know that this is an aldol addition reaction, you have your alpha carbon and your beta carbon, and the beta carbon has to be a hydroxyl. So pretty quickly you can see that this is the only possibility. So again, this is an aldol addition, not an aldol condensation. All right, let's move on from there. And let's try question 11. So that would be the enols and enolates chapter. So this is enols and enolates. All right, let's move on to question 11. What would be the major organic product of this base catalyzed reaction? So again, we have another aldol addition reaction, don't we? Right, this compound is has no enolizable protons, where these are the only enolizable protons between both of these molecules. So you would end up forming this enolate. You would end up with this enolate, which is going to act as your nucleophile. And again, since there's no heat, this is an aldol addition reaction. I mean, you could probably just look through these immediately and say, well, let's see. It's not going to be this compound because that's a condensation. Here you have your alpha that has the hydroxyl on it. That's not correct because it would have to be on the beta. You look over here, you got two carbonyls. That's not right. Here you have alpha, you have your alpha carbon and your beta carbon, which has a hydroxyl. So it's got to be D. I mean, you don't even have to draw a mechanism here. You just have to know a little bit about the chemistry. All right, so you draw the enolizable proton, and then you draw your electrophile, which is this compound here, and you end up doing a nucleophilic attack like that. You end up with this compound, so draw this guy. We've got our alkoxide here. We have our tert-butyl over here. Then after a proton transfer, we end up with this compound right here, D. There you go, just a plain old aldol addition. Question number 12 says, which of these reactants can be used to make this compound by an intramolecular aldol reaction? Now, this is an aldol condensation, isn't it? Right, because we have a double bond between our alpha and beta carbon of our carbonyl. So this is an aldol condensation. But either way, all we have to do is look at these compounds and determine, well, which one of these could you use to make this compound? Right? So one of the easiest ways to solve this kind of problem would be to do it by retrosynthesis, right? Is to break this bond here and then to say, okay, well, my starting material would have to look like this. Oops, I can draw it a little better than that. Let me just clean that up a little bit, like this, and then I have a carbonyl, and that would be my starting material, right? Which is B, right? So we just solved that by a retrosynthesis, and I showed you how to do that, a couple times in the enols and enolates chapter. So again, just a retrosynthesis, and you could practice drawing up the mechanism for this if you wanted to. Just an aldol condensation that occurs intramolecularly. So for this, you'd need to have, sodium hydroxide, and you'd have to heat it up, okay, to get the condensation reaction to occur. Let's take a look at number 15. So number 15, which set of reactants in the presence of a basic catalyst could be used to prepare this compound? So if we want to make this compound, look, we're in the presence of a base, right? So we're treating this with a basic catalyst. Again, you can see this is the product of an aldol condensation reaction. So all you have to do is break this bond here, right? And you can do the retrosynthesis just like I did in the last question. So what would your starting material be? It would be acetone, would be one of them, and the other one would be benzaldehyde. There you go. That's it. So you need acetone and benzaldehyde. Is that one of the answers? Better be. Yeah, it's C. So again, just doing a little retrosynthesis here. And again, this is an aldol this is an intermolecular aldol condensation. Question number 18. Let's see here. It says, if this steroid, tetracarboxylic acid, is heated, which carboxyl group will be readily lost as CO2? I want it carbon 2, 5, 13, or 15. Could anybody tell me? There's one of these that if you heat it up, it's just going to poof, blow away instantaneously. Yeah, it's going to be the one. Oh, I can't see your answers. Let me scroll down here. Does anybody have an idea here? Think back to the malonic ester synthesis. You know, which one of these is just going to poof, blow away in the wind once you heat this up? Does anybody have an answer? No? Right, you need to have a carbonyl, okay, and it's going to be the carboxyl group that is alpha to the carbonyl. All right, we talked about this when we looked at diethylmalonate type chemistry, right? If you have, let's say, you know, if you just draw your carboxylic acid out like this, your proton over here, draw this like that, right? You end up doing a proton transfer like this, okay? And you do that, and you end up making an enol like this, okay? Which is going to tautomerize to give you the ketone, but in the process, you end up losing CO2, so you lose CO2. So it has to be a carboxyl that's alpha to a carbonyl. So the answer is the carboxyl at carbon 2. Question 21, what would be the major product of this reaction sequence? So let's see here. We've got ethyl benzoate, which is the first compound, and then we've got ethyl propionate, which is the second ester. We're taking those and we're treating them with sodium methoxide and then water and acid. This is just a Claisen reaction, isn't it, right? Because you only have one enolizable proton between both of these molecules. So you would do the proton transfer here to make the enolate. So you'd end up with this enolate, draw the negative charge here, right? You end up with this compound, and then that's going to do a nucleophilic attack on this carbonyl here, okay? And then you're going to produce an intermediate, which is going to look like this. I'll draw it as neatly as I can. So you end up with this guy here, and you have this oxygen, you have this alkoxide here, and then you have your phenyl over here. So then this is going to produce a new double bond, and you're going to lose the alkoxide as your leaving group, and then that is going to give you this compound. So let me draw it out here. I know that there's not a lot of room, but hey, we're organic chemists, we can make do, and then you have your phenyl over here. So which one of these is the correct compound? I'm just looking at them myself. So the answer is B. And I was tricked by C when I first looked at it, but you see the oxygen is in the wrong position here. So the answer is B, and this is just a regular old Claisen reaction. If we look at 22, so this is an product of an intramolecular Claisen, so this is just a Dieckmann reaction. So we have on our alpha carbon, we have our ester over here. And so I think the best way to solve this is just to do this by a retrosynthesis. So if we break this bond here and just think about this in terms of retrosynthesis, we would end up, let me just draw it all the way down here. You would end up with something that looks like this. So you've got this carbonyl, and then you've got an ethyl group over here. Then you've got, I'm just counting from here, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And then on the 6th carbon, you've got a carbonyl, and then you'd have another ethyl over here. So which one of these? 1, 2, 3, 4. So 1, 2, 3. So this is wrong. So this one doesn't have enough methylenes. 1, 2, 3. This one, you can see the ester is jacked up over here, so that's wrong. So the correct answer is D. So we just solved that using retrosynthesis. Again, just a Dieckmann reaction. Let's see here. Question 27. Question 27. Says, which compound would be produced by this reaction? So again, we have an ester, and we have this diester here. So this is dimethyl oxalate, which you would call the second compound. We've only got, again, one enolizable proton, which would be this one here. So you'd end up with this enolate, this guy here, which is going to act as a nucleophile here. And then you're going to end up losing the methoxy. And so when you do that, you end up, again, you just end up losing this alkoxide here after you form the tetrahedral intermediate. It goes away, and then you end up with this compound. So let me just draw it as neatly as I can. And then we have a carbonyl, carbonyl that reforms. We have another carbonyl, and we have O-methyl like that. And so that is going to be A is going to be the correct compound, right? This methyl group is this one here. There you go. Just another nucleophilic acyl substitution. Let's try one more from this section. This is question number 30. Which of these reactions could be used to make a beta keto ester? So if we want to make a beta keto ester, in the first one, there's only one enolizable proton, so you'd end up with this enolate, which is going to do a nucleophilic attack here. You're going to end up losing this methoxy group. That is going to give you yeah, it's going to give you an enolate, which I can draw for you. It's going to give you this right here, where you end up with this doubly stabilized enolate. Okay, and then that's going to react with the ethyl bromide. So then you've got the ethyl bromide, and that's just going to do a nucleophilic attack like this, and that's going to give you the desired product. Same thing in number 2. You would end up forming the enolate right here. Again, it's the only enolizable proton. So you end up doing a nucleophilic attack here. You lose this leaving group, but you've already got this ethyl group here. So that's going to give you the product. And then the last one, you've got only one enolizable proton. That's this one here. You have a carbamate, which has got good leaving groups on it. So you're going to end up losing one of those. And that will give you the same compound. So the answer is all 3 of them will give you that compound.